for investigation 11B, which is about tornadoes. And I just recorded the video for investigation 11A a few minutes ago, kind of stammered my way through that one. And what I'm going to do in this particular video is focus a little bit more on that Logan County tornado that I mentioned in my video for investigation 11A. So we're going to kind of dig in, talk about this tornado a little bit, and kind of do a bit of a case study. So why don't we get started? And I'm going to begin the slideshow right now. So again, this is about tornadoes, but again, this is going to really be just a case study about this particular tornado. So what the AMS first does is it kind of gives you the setup of the day for our Logan County tornado. And this is actually a surface map from 12Z on the 9th of December 2023. And next to it is a map from the Storm Prediction Center. And this is for the same time, basically taking a look at 500 millibars and heights and winds. You know, the thing that I find really interesting about the Storm Prediction Center is that the quality of their maps is not great. And so you can see that the numbers are kind of pixelated and the wind information is a little bit pixelated, and I apologize for that, but it's just not a great map produced by the Storm Prediction Center. But I do want to point out a couple of important characteristics that we see on these maps. First of all, I wanted to talk about vertical wind shear. I mentioned vertical wind shear briefly in the Investigation 11A video when I talked about storm organization. And I talked about single-cell thunderstorms and multi-cell cluster thunderstorms and squall lines and supercell thunderstorms. Now, these sorts of storm organizations really are driven by differences in vertical wind shear. Vertical wind shear is defined as the wind speed and direction change in the 0 to 6 kilometer layer above the Earth's surface. We don't really talk about directional shear in our class. We really focus more on speed shear. And what we see in general is that when you get vertical shear greater than 40 knots, that typically provides an environment where you can get rotation. Now, before I move on, let me say what I mean by 40 knots of vertical wind shear. What that 40 knot number means is that the difference between the lightest winds and the strongest winds in that 0 to 6 kilometer layer, the difference is at least 40 knots in this case. So when you've got a wind speed increase going up off the deck up to 6 kilometers of 40 knots or more, that is typically sufficient vertical wind shear to create rotation. Now, I'm not going to talk about how that rotation is created, but I will say, because it's going to be important when I show you a slide in a few minutes, I will say that the wind shear itself actually generates the rotation along a horizontal axis. In better words, if you think about tornadoes rotating, the funnel rotating, that rotation is occurring about a vertical axis. The wind shear actually provides us with rotation about a horizontal axis. So something else has to actually be going on to actually tilt that rotation up from its horizontal axis to that vertical axis that we see when we get our tornado. And again, I'll talk about that in a few minutes. But again, vertical wind shear is essential. When we took a look at our single cell thunderstorm in the Investigation 11A video, the reason that single cell, does not produce severe weather is because the wind shear, the vertical wind shear, is typically 20 knots or less. There's simply not sufficient shear to actually provide for rotation. And in fact, the shear is so weak that you really don't get any sort of structural organization whatsoever. You just get those random single cells. So again, you need strong vertical wind shear to produce an environment in which you can get rotation. The other thing that's really important is that you have high dew point temperatures. High dew point temperatures basically mean that you have a lot of water vapor in the air. So when you get strong upward motion, what will happen is the air, the parcel, which is cooling dry adiabatically, will very quickly saturate as a result of expansional cooling. And then as it continues to rise, you'll get that latent heat release as the vapor condenses to form cloud droplets that will actually help to drive the parcel up even more quickly. So the high dew point, again, leads to lower altitude condensation and that latent heat release. Now, if we take a look at our maps, this is a December example. So this is not exactly what we're used to when we think of severe weather outbreaks. We think of hot temperatures and dew points in the 70s, and this is not the case at all. But what you'll notice for our couple of station models in the Gulf Coast states going up into Tennessee is that the air is nearly saturated. So for example, here in South Central Tennessee, you've got a temperature of 55, a dew point of 55. The air is actually saturated. In far west Tennessee, you can see a dew point depression of only 1 or 2 degrees, and in Alabama, again, 2-degree difference between the temperature and the dew point. So while it's not hot, and maybe the absolute value of vapor in the air is not tremendous, the fact of the matter is that when you begin to lift air surface-based upward, and you get that exponential cooling, the air very quickly is going to saturate so that you can get cloud formation and a latent heat release. Now, before I move on to my 500 millibar map, I just want to mention this front. And I showed the cold front actually entering Tennessee about 6 hours later than this. I think I showed an 18Z map. And so when you get an organized front like this, pushing into a humid air mass, a humid unstable air mass like we had in Tennessee, the front provides a very organized area of lift. So you get organized lift along and ahead of this cold front. And what happened was this cold front, as it pushed into Tennessee, led to the formation of the squall line that we actually discussed in the 11A video. And that squall line actually had the thunderstorm embedded within it that produced the tornado that we're going to focus on in this particular investigation. Now, if we go back to our wind shear, if you take a look at the wind speeds in west and central and middle Tennessee, I don't want to call it central because it's middle Tennessee, in west and middle Tennessee, you can see that the winds basically are anywhere between 0, calm, or 10 knots and 5 knots down here in Alabama. So surface winds are really, really weak in this area. If we take a look at winds at the 500 millibar level, which is actually below the 6 kilometer level, you can see that the height here in Nashville is 5.7 kilometers. So this is actually below the 6 kilometer mark. And you can see that the wind shear is at least 50 knots. The 0 to 6 kilometer wind shear is at least 50 knots over Tennessee. So there's more than sufficient wind shear to actually produce rotation in this particular scenario. So you've got a strong front pushing into an air mass that's extremely humid, and you've got strong vertical wind shear. So basically the ingredients are all there for some sort of severe weather outbreak. And as we'll see, I think it's in our last slide of this particular video, the Storm Prediction Center actually did put out a tornado watch for a very large area in this area in Tennessee, Alabama, up into Kentucky. So again, the high dew points actually lead to enhanced updrafts. That's my last bit of wording on this slide. So this next slide, which is provided in the investigation, I think is probably a bit much for our class, to tell you the truth. But let's just go through it at least in a little bit of detail. What we're seeing here is basically a sideways view into a supercell thunderstorm. So the way to think of this is to imagine that you're taking a look at this and you're looking at your screen, and imagine in the left, you're southwest of this supercell. Now imagine you're going into your screen diagonally from southwest to northeast. That's how you want to actually look at this particular graph. Now, if we take a look at this, what you'll see is we've got the main tower of the storm, and then we have 2 downdrafts actually being produced by this supercell thunderstorm. This first one, which is produced by the rain in the main cell, is called the forward flank downdraft. And so this is a gust front, basically the boundary between the warm, humid air ahead of the thunderstorm and the cool air that's being produced by the rain that's falling from the cloud. This is called the forward flank downdraft. And then what we have is something called a rear flank downdraft, and this is actually produced by the rotating mesocyclone, which is right where my cursor is right here, circling around counterclockwise. And what the mesocyclone is doing is it's taking some cloud level air and it's twisting it around the south and the west side of this supercell thunderstorm. And it's actually causing what we call a hook of clouds. So here's this hook of clouds, and here is the downdraft that's actually being produced by the rear flank downdraft that's associated with this hook of clouds. So what you'll see basically are 2 downdrafts that basically wedge air ahead of the storm into the supercell. Now this air, as a result of the really strong vertical wind shear, is rotating about a horizontal axis. And then as it is forced up into the supercell thunderstorm, the rotation is basically tilted up from its horizontal axis into its vertical axis. And then from there, what you need to do is you kind of need to follow this air, some of which is going up into the supercell, rotating counterclockwise, and some of which is just heading back down again in the rear flank downdraft, also rotating counterclockwise. And this actually is the air that's leading to the formation of our tornado. So again, a lot of arrows twisting all over the place, but this is just kind of gives you a schematic about what we see inside of a supercell thunderstorm that is tornadic. And you can see the overall storm motion from southwest to northeast being steered by our upper level winds, and we talked about steering flow in a previous investigation. Now, before we move on to our Logan County tornado, just a couple of more details about how it is that we assess the intensity of any given tornado. So there was a professor at the University of Chicago back in the 1960s and 70s. His name was Ted Fujita, very, very famous meteorologist. And what Fujita did was he did a number of field studies as well as lab studies with wind tunnels to try and assess the type of damage that would be caused by winds associated with tornadoes. And what Fujita did was he ended up coming up with a 5-step, actually a 6-step scale that basically assessed the types of damage to various ranges in wind speed from basically the weakest tornadoes called an EF0 or an F0 actually for the Fujita scale, and going all the way up to an F5. And so what Fujita did was he developed and published his scale in 1971, and it was called the Fujita scale. And so Fujita scale went everywhere from EF0 or F0 all the way up to F5. I keep putting that E in because that's what we use now. But the original Fujita scale, again, it had damage patterns associated with specific ranges of winds going from 0 all the way up to 5. Now, what Fujita basically was not able to do was to really assess really terribly accurately the types of damage that actually were associated with his ranges of wind speed. And so over the years after the Fujita scale was published, basically as a result of field observations following tornadic outbreaks, where that scientists realized that the damages that Fujita basically came up with and assigned to specific wind ranges, the wind ranges were not quite right. And so a lot of research basically went into refining Fujita's original scale, and that led to ultimately what we see here in Table 11b1, which is the Enhanced Fujita scale. And the Enhanced Fujita scale was published in 2007, and it's what we use today. Now, the great thing about the Enhanced Fujita scale and the Fujita scale is the Enhanced Fujita scale, the scientists didn't change the damage for each category that Fujita came up with. Instead, what they did was they reassigned wind ranges. And so what the Enhanced Fujita scale actually found was that for the really largest scales, basically the Enhanced Fujita winds were a little bit stronger than the original Fujita scale winds. But for the larger tornadoes, as we go from 1 to 2, 3, 4, and 5, for the major tornadoes in particular, Fujita overestimated the wind speeds that caused the damage that he expected to be produced. And so what the Enhanced Fujita scale does is it basically takes these wind speeds down a little bit. They still cause the same damage that Fujita expected to occur with his stronger winds. It's just that it turns out that the wind speeds that cause that damage are not quite as high. So this is the scale that we use today. Again, it's still a 6-step scale all the way from 0 to 5. Here are the wind speed ranges. And you can actually go online again and get a lot more information for what light, moderate, considerable, all the way to incredible means. If you actually do a search for the Enhanced Fujita scale, you'll actually see the descriptions in terms of the type of damage that is caused by winds in each of one of these ranges. And by incredible, basically what that means is that there's nothing left standing. So houses, for example, that would be on cement foundations, all you would have would be the cement pad. All right, so again, you can do a good bit of investigating beyond what I'm doing here on your own. Again, tons of stuff online. All right, let's get to our Logan County tornado. Again, this is part of a larger tornado that was called the Clarksville tornado. It was a long path tornado. It was on the ground for quite a while. We're just going to focus on the part right along the Tennessee-Kentucky border. And you can see the details of the Logan County tornado right here. So again, the 9th of December, 2023, this tornado was on the ground for just a little bit longer than half an hour, so 34 minutes. The strongest winds during this particular time classified as EF2. So you can go right back here to EF2, and you can see that the winds were between 111 and 135 miles an hour. Now, I want to make it clear that there is no anemometer that actually measured these wind speeds. The National Weather Service came up with this wind speed range based on the field work that was done after the tornado passed through this area and by looking at the damage. So based on the damage pattern, the National Weather Service basically classified it in this wind speed range. So again, 100 basically EF2, estimated peak wind speeds were 115 miles an hour. Here's the path length, that's a little bit shorter than 23 miles, and the maximum width of this tornado was 250 yards. So think about that. That's 2.5 football fields wide. So that's really, really wide. And luckily, this is a very, very rural area, so there were no injuries or deaths associated with this part of the tornado. I do believe the Clarksville tornado actually did kill a few people, unfortunately. Now, you're going to be asked in the investigation to actually figure out the speed of this tornado during this particular period of time. So in order to do this, you have to do a bit of division. So you have to put the path length, which are actually given in the numerator of this fraction, and then in the denominator, you have to actually put the amount of time that this tornado was on the ground. And you don't do it in minutes. You have to do this in hours. So you have to figure out that 34 minutes on the ground. What is 34 minutes in an hour? So for example, half an hour, 30 minutes would just be 0.5 hours. So the denominator here is going to be a little bit bigger than 0.5. You could just basically do this by dividing 34 by 60. 34 minutes divided by 60 minutes will give you the fraction of this is in an hour. And then you do the division and you'll come up with your correct answer. Okay, this is a really, really nice image of the tornado in base velocity mode for Doppler radar. So Clarksville is, I can't remember exactly where Clarksville is. I think it's right off of the left side of the map here. You can kind of see the radios kind of shooting out right here. So Clarksville is probably right about where my cursor is. And what you can see on the north side is that you've got very strong motion toward the radar. And on the south side, looking at the reds, you have very strong movement away from the radar. So you've got toward here, away here, and if you were to put a little pinwheel in, what you would get would be very rapid counterclockwise rotation, indicating the presence of this tornado. So again, Doppler base velocity radar is really, really useful in identifying the rotation in a storm. Now this is the last slide in the investigation. I just want to show you the watch that was actually issued by the Storm Prediction Center that actually was part of what we saw on this day on the 9th of December. So this was actually issued at 11:35 in the morning Central Standard Time. The actual tornado, which again I'm going to try and find, here's Clarksville. I believe the tornado occurred right about where my cursor is. So this tornado occurred 2.5, 3 hours after this watch was issued. And so this watch actually was in effect until 7 p.m. So it was a long duration watch for this area. So this came out from the Storm Prediction Center. And for the actual tornado, if you take a look, you'll see that the tornado warning, which was actually issued by the National Weather Service in Clarksville, I think, was actually just for this little area right here where the tornado occurred. It's hard to see, it's not even a full county wide, but you can see that just this small area was under the tornado warning during the period of time that the tornado was on the ground. And you can get a little bit more information about the tornado warning right here. Now, I will say that this is a really nice graphic. The National Weather Service and the Storm Prediction Center do not put out graphics that are this nice. So this particular graphic, I think, ultimately came out maybe from the National Weather Service from, again, I don't see pictures like this when I see severe weather reports in real time. So I'm not quite sure where this came from, but this is nicer than what you'll typically see on Storm Prediction Center and National Weather Service sites when we actually have a severe weather outbreak in progress. Okay, this is pretty much everything I'm going to say about tornadoes here. If you have any questions whatsoever about tornadoes, and in particular this particular outbreak, by all means feel free to post your questions to the discussion board or ask me live during my office hours, fall session, Wednesday evenings, 7:30 to 8:30, or Sunday afternoons, 2 to 3 p.m. But that's it for tornadoes. I'm going to end this video now. I'll post it on Canvas and you'll receive an announcement when it's ready for you to view.